This.
There we go.
Yeah.
Go for it, Bob.
Okay. I'm Bob Goddard. I have been around here, around Northwest C++ since its inception, just about. I want to talk about something that's related to last August's talk, but it's not the same talk. It is a larger scale to this. I want to not just talk about how you make C++ and Python play nicely together, but why and how you package them as a product and how you document it and how to handle scale and portability and all of those issues that you need in order to develop something that people will actually use. Okay, now, first of all, I'm going to treat my career product, the Sonar simulation toolset, as basically a black box. It contains a bunch of code that I'm going to wrap and package as a library in C++ and Python. It was largely under Navy funding, so I can't release it as a package to you. It's just, you think of it as a black box. I developed it. I had great support, and I still have great support from Applied Physics Lab. The work here, though, is mine. It's not funded by DoD. Although UW did provide the computer and the software and technical support and encouragement. UW holds the copyright. Okay, outline. I'm going to start with, what is it? What is this thing that I can't get to the why until I tell you what I've got and where I want to end up. So I'll start with that and then move on to tools and other details in actually doing it. Now, the starting point is a package. It's a computer program whose purpose is, if you look down, can you see my arrow?
Yes.
My pointer. It's down here. The output is a signal, something you can listen to or feed into a signal processor. And in order to get that signal, you have to know about the ocean and the things that are in it, and the things that are receiving the sound, and the things that are producing sound, and all of these things that happen to the sound in between. These things around the edge are models within the system, describing things, real things in the ocean or the ocean itself. And the things in the middle are the active parts, the computational pieces. There are pieces for target echo to generate, and these things generate signals. But they use all of those other things. And that's probably enough to just keep it in mind, though, that it's a pretty big system that has to put together a whole lot of detail in order to produce one relatively simple output. The signal can have a whole lot of channels in the signal, because listening devices in the ocean can be rather large and complicated. Okay. Now, the way SST is designed now is that it's got a parser at the front end, and it's a symbol table associated with the parser. The descriptor, there's one descriptor per class in the working class set. But all of this parser front end, I would like to replace it with Python. The script language that parser parses looks like this on the right. This is a description of a particular kind of a signal. And this delay. This is another signal that tells by how many seconds it's going to delay. So I'm going to apply a time varying delay to this signal that's got 2 tones in it, and copy it to a sound file. And so the delay generator is this var delay. This is one of those computational things. This is a relatively low level one. These are used within things like target echoes. That takes as its delay, it's got this thing, this delay goes there, and the in signal is there. The thing to be delayed is there. But the only place where any action happens, any computation happens, is on copy when this copy signal command is executed, which reads successive buffers from this delay generator object, which does the delay and computes the signal and puts it in a file, which is this out signal. It's a sound signal file. The language is object-based. It's not object-oriented. It's object-based in that it deals with objects, but the classes to which the objects belong are defined by the language. Mostly it describes data. The ocean, the receivers, the sources, the scatterers, the signal generators, such as target echo. Oops, I didn't mean to do that. Okay. The scripts are mostly these things that construct data in memory. Then there's one important verb in the whole language, copy signal. Very incomplete. It's a data description. It's almost entirely, it is a data description language. No decisions, no loops, no arithmetic, one scope. And the recursive descent parser that I wrote back in 1991 is brittle, and I dare not touch it. It breaks whenever I touch it. Okay. Now, the way I originally envisioned SST to be used is that you make a file of these commands and in an editor and feed it into SST, and you compute the signals, which go into another file, and then you either listen to it or analyze it and plot it, usually in MATLAB. Real simple idea about how it would be used. Little did I know that the more common usage pattern in real life was that the parameters needed to be computed because they relate to one another, and the receivers are large, so you need loops in order to generate them, and the trajectories are complex, and you want to run it repeatedly with many different scenario versions. So what you actually do in order to use it is that you write a MATLAB script, a set of MATLAB scripts, and these can get quite involved and then have some way to edit the parameters of that script and have it generate the commands and any source signals that you need, and run that through SST, and it goes into a file just as before. But then there's another usage pattern. It's got the scenario, got the script generator, but you want to do a closed loop, because the output from the signals go into signal processing and some control chain that changes where things are and goes back into this scenario generator, which can be MATLAB or something else, and generate some more commands and some more source signals and go through the loop again. And that's useful for autonomous systems and behavioral models. And then usage pattern 4 is where you put a human in the loop. These are some of the same things, except that you have a simulator of a duty station that an operator sits in front of. And it still has to have a dynamics model and a scenario generator, and it's another closed loop. You'd use this pattern for training and tactics development and evaluating changes to systems. But to do this, you need something on order of real-time performance. what I'd like to do is eliminate all of these files. These things that are in light brown, or whatever you call that color, are files that have to be written and read and parsed. What I want to do is enable a user to write a simulator for a specific system and for a specific purpose in C++ or Python, and run it through libraries that are the core of SST, and do all of this through function calls. Now, whether this stuff over on the right is part of the same process or not is TBD, because we're not doing this yet. But at least the simulation, the signal simulation part that produces these signals, is one or a cluster of threaded cluster of threads, we would hope. But it's one application, and the data is passed through function calls instead of files. And that's where I'd like to get. So the desired endpoint is a set of C++ shared libraries and headers, so that you can point at what is the computational core that you need in order to generate sound that you can listen to or operate on. That is accurately simulates the sound that you would hear if you put this system in the water. Plus, now it turns out that there's some history here, because back in 1990, when I was first doing this, the very SST 1.0 was sort of like this, except that it was C code, and what I was asking the users to do was generate headers, was produce headers that set up the scenario as C headers. That produced cries of anguish from my users, such as my sponsor, who said, "Yeah, no, I don't want to do this." That's why I invented this language. But now I want to go back to that, but with a lot more infrastructure to make it easier to use. But because not everyone wants to go as deep as to directly write C++ to call the C++ shared library, I want to wrap it in a Python binding to replace this command language, but with something much more powerful and extensible, so that users can add subclasses of existing base classes, either in C++ or Python. It's got to be well documented, and I have recently fallen in love with Sphinx as the documentation engine. That I also use Doxygen based on, and then there are a whole lot of Doxygen comments in all my code. And what there exists now is the SST web, which is a whole lot of hand-hewed HTML, handwritten HTML, and an SST science report, which is PDF from LaTeX. And a whole lot of examples already exist, and I need to do more. And we need new tutorial now for tutorial material. The transition is to use existing SST scripts in a Python environment, so that you still don't have to write and read the output files, but you can still, if you have existing SST scripts, you can use them. And we hope, I would like to provide a translator from this SST language to Python, constructor calls. Packaging, wheels, conda. I'm pretty sure that's what I want to do, but I haven't done that yet. The SST main program will remain because I do have existing users. Why do I want to do this? Well, I have a personal reason. Next month, or a month and a half from now, I will be 75 years old, and no one else has proven willing to pick up this. I want it to remain this product. I want it to be useful and improving after I'm out of the picture. And no one I know will or can or should try to maintain the front end, the SST parser. Publishing and documenting the underlying classes will enable someone to carry on. Now, my employer, Applied Physics Lab at the University of Washington, needs a reason also, which is to expand the user community beyond the Navy, particularly education and research. And the Navy needs a reason, since they're the ones who paid for most of the development over the years, to reduce the cost of applying realistic underwater undersea sound simulation. Okay, now down to the nitty-gritty. I've chosen SWIG as the tool to make the binding between C++ and Python. Now, PyBind 11, the speaker last August talked about this, is much simpler. And it's C++. You don't have to learn another language, although it's, you know, you can recognize all of the syntax as C++. Oops, I did it again. What did I do? SWIG does somewhat more. SWIG is not just a set of libraries. It's also an executable that parses C++ header files, it parses C++ code. It actually has a piece of LLVM in it, and comes with a whole lot of other SWIG interfaces for things like the standard library, the C++ standard library. And the output consists of C++ interface code that compiles to a shared library, which is a Python extension model. That's the same sort of a thing that the output that PyBind 11 produces, but SWIG also produces a Python wrapper, a .py file, and SWIG also can be used as a front end for other scripting languages that accept C or C++ code as extensions. Now, the absolute minimal code that you need, an example that I'm doing is that I'm assumed to have a model, to have a header file that defines a class, and that it's got a constructor and two functions of integer, and it's got Doxygen comments in it. And all you have to do in order to wrap that in SWIG is to name the module. The first include with a £, is placed verbatim at the top of the generated C++ file, and the other include with a % in front of it is what SWIG crunches on. That's the input to SWIG, and SWIG takes that, parses it, and but what that means is that SWIG knows the names of things. PyBind 11 does not. PyBind 11, the binding code, if you want to make a name for the thing that's the Python version of the class, you have to name it. If it's the same as the class that you started with, that doesn't matter, because you still have to name it in the binding code. If you're going to change the names anyway, such as if you use your different naming conventions, then you have to do the same stuff anyway. But you do have to add the names in the binding code. You can change the name if you want to in SWIG, but it takes one line to change a name. then what PyBind 11, and if you want doc strings, I'll get into this in more detail later, but if you want PyBind 11, if you want doc strings in your Python, then you have to put them in your binding code up here. Tell somebody what it's for. Whereas if you already have Doxygen comments, which I do, lots of them, then Doxygen will pick them up and put them into the Python doc strings where properly formatted, where SWIG can pick them up. And we'll see that in great detail later. Naming conventions. This isn't horribly important, but I've decided that I'm going to keep the same naming convention I'm using in my C++ code, rather than use the Python convention, where everything is lowercase with underscores. And there is some precedent for that. One of the major, best used, and excellent libraries that you can get for Python is the WX Python, the app generator, basically, which is based on the C++ WX widgets library, which is also published, and it uses the same convention. So I'm not going to use that. Also makes SWIG binding code simpler if I stick with the C++ names. Okay, now the language, the SST command language is primarily deals with creating objects. So the constructors are key, and so they take the role. The language takes the role of constructors, but in the old code, the SST front end that parses the SST command language creates objects using a default constructor, and then sets its attributes, and then calls an init to check to make sure it's a legal object, and that's how it creates an object. There usually are full constructors, but they don't always exist. And my example is something I've talked about in a previous talk. What a snapshot is one element of a trajectory that describes how an object moves through space in time. But you can, and the old version of the snapshot constructor was essentially this. You just fill in the attributes of the member functions, member data. The new way that I need to do in order to support Python is you really have to have a full constructor that also acts as the default constructor. So everything has default values. And so that's what I had to do. I had to ditch both the default constructor and the old full constructor and make one constructor that supplies default values. A constructor like this, I have found, needs to be added to each public class that I want to wrap. And in fact, given that I have not published the C++ before, users of SST don't see my C++ code at all. They just use the command language. But I would like to make the C++ open to my users as well as the Python. And this actually is what you need for both of those. You have to have a real constructor. And in order for the Python, you need it to have the default values exposed. That's not what I want to do. Okay. And now here's a piece of SST command language. This is SST command language that creates a snapshot object, gives it a name. It fills in the attributes of that object, a time, a position, which is a vector, a velocity, which is another vector, an orientation, which is another, there's another type that's got heading, pitch, and roll, and an orientation rate of change, which also has heading, pitch, and roll. Now, the way I have wrapped this is to make the Python constructor look as familiar as possible to people who already are accustomed to the SST script. So you have to import the geometry module and give it a nice short name, and the snapshot gets a time and a position. It gets a vector, and the velocity is another vector, and which is also wrapped in this same module. And the syntax is a little, oops. The syntax is a little different. You've got braces here around this, and these are parentheses, and you have to put commas in here, and there are either the end of the line or semicolons here. And you have to put in the module name at the beginning of these, but this looks really familiar to somebody who's accustomed to this up here. Now, and as soon as I make the new constructor, then SWIG will produce Python that allows me to use this syntax to create a snapshot. Great. But if you want a simpler constructor syntax without the class names here, previously I had to put vector here and orientation here and here. You had to name the class name the type of the argument. If you want to avoid naming the type of the argument, the script will do that. You can just give it a triple of numbers, and it knows to interpret it as a vector or an orient, depending on orientation, whichever context it's in. But in order to do the same thing in the SWIG generated, and I have done this, it's a lot harder. But what you have to do is but SWIG does provide the tool, and the tool that SWIG provides is called a typemap. And this looks, I don't want to go through exactly what this is doing, but this is the sort of scale of thing you have to do in order to have an input argument interpreted as if it's a tuple or a list on the Python side, you want to have it in this context interpreted as a capital V vector, a 3 vector, which is one of my types, or an orientation. And this is the type map for vector. And there's another one that looks almost exactly the same for orientation. Now, if I were going to and from something that's already in the standard library, like a little v vector, standard vector, or complex, or something else that's there, chances are there's already a type map for it, and you don't have to worry about that. And I've only had to do this a very few times so far. And I've done most of the low-level things, and it's the low-level things that you want to do this for. Excuse me. Now, there's some other things that you need to do a complete job in the SWIG, because some of the class members you don't want to expose to Python, so you tell SWIG to ignore it. Some of the operations you want to be replaced by standard Python operators. So you don't want an inserter for to do output. What you want instead is this representation standard function built into Python that every Python class is supposed to have, and you can produce this thing. Now notice it returns not a Python string, but a standard string, but SWIG knows how to transform this standard string to a Python string. So in the end, the SWIG generated code actually returns a Python string to Python, as is required for this repr standard function operator, really. And in addition, template specializations are mapped to plain classes. You have to do this because Python doesn't have templates. And the setters and getters are wrapped as attributes. In fact, in this particular thing, there are two overloaded functions. There's a setter and a getter, both of which are called position with a capital P, with one with an argument and one with no argument, and that returns a value. And one with an argument that returns void, and one with no argument that returns a value of type vector. So you glom those together into an attribute in Python so that you can set it as if it were a data object, but it is actually set through the setter and gotten through the getter. Is that more or less clear? Okay, but you have to put it together, but it's easy. I mean, you just put in a line like this. If you have a setter and a getter and you want to make an attribute, you just put in a line like that. Okay. Now we get to, this is a large part of the reason that I chose SWIG rather than one of the C++ only tools. This is similar to what my existing code contains. It's got this. Here's a class snapshot, and it's got this new full and default constructor, and each of these arguments has some code with a special comment attached to it. 3 slashes and a less than means this comment is Doxygen information that is attached to this argument, and the 3 slashes is Doxygen information attached to this function, and this is attached to this class. And now I want to make some, yes, and here's what Doxygen produces. Out of that, it will talk about snapshot. It will let's see now. Yes, this is a okay, class snapshot. There's an inheritance diagram. There are a couple of subclasses of it. And there's a collaboration diagram. These are all of the other classes that snapshot works with. And you get, the public types are up here and the public member functions are here. And here's snapshot. In fact, this is the constructor. That's the full and default constructor. That one line, that top line is there. But if you open this and click on more, here's all the details of how that function is to be used. I lied a little bit. I left off this last argument just for simplicity, but. So there's one. In reality, there's one more argument, but I don't want to have to explain that argument, so I didn't show it before. But this is what Doxygen produces. Real useful for people who want to use the C++ code. Okay. Now, SWIG takes those same Doxygen comments and inserts them into the inserts them into the doc strings. Python has documentation within the code, and that persists as part of the code, and in fact, it has a lot of this has syntax to it that's somewhat similar to Doxygen's syntax. It's what's it called? Markdown, or there's something else that it talks. There's another name for that. But all of the same information is here, and within the Python class. But if you then run Sphinx on that to generate documentation for the Python, that's here. Now, here is module SST Pi, and I can go to the geometry module within that, and there is a snapshot within that. And here are all of the operations on that, including this init. Init is essentially a constructor in Python, and it's got all the same information. It's got this stuff all comes from the documentation string, and this stuff comes directly from the code. And this is all from the same information. I didn't have to rewrite any of this in order to get two different highly readable sets of documentation, one for the C++ and one for the Python. Real cool. So this is one of the coolest attributes of this system. Okay, and this is just a blow up. This is this particular thing. It shows what. That's just a screen capture. I'm going to go on from that. Okay, so that's enough about the tools. Shared libraries are, as almost everyone has worked with them knows, a pain to work with, because the app everything has to know where they are, not only at build time, at link time, in order to link to them, but also at runtime, and they have to know how to find them. And particularly in Windows, this is hard to do, at least for me. But I studiously avoided shared libraries until this project. And statically linked the executable because I could, and it was far simpler to deal with. You can move the application from here to there, and it'll still work. So the SST Pi here's the organization of this thing that I've built, which is a package, a Python package. It's a library that's got these init functions, and they actually do things. I'm not going to get into it. They can be blank, but these are not. The geometry one that we've been dealing with, the output from SWIG consists of two things: a Python file and a shared library. And this is the version that you get on the Mac that it looks a little bit different on Windows, and it looks about like this on Linux. And these together, this is the sort of the front end of the module, and it imports this version, the low-level version that goes to the C++ code privately, but the public sharing. Public interface is defined in the Python. But this had these SO libraries also have to be linked at runtime to the dynamic library that's got the guts of SST in it, and to third-party libraries from Boost and MKL and some others. And managing them at runtime is a pain, and on Windows, I can make it work with a great deal of effort, and I would love to learn how to do it more easily and automatically. I think what it means is that on Windows, you simply do not move a package from here to there. You have to then run something on it in order to groom it so that it will know where itself is. I wish that were not the case. Okay. There's also documentation, and I have, as part of this, discovered Sphinx, and I am a believer. It's a great tool. The output here, I've written some documentation, not enough, but there's part of it that is the reference part. The ones that says reference HTML. Here I can show. I mean, these are the files that Sphinx generates, and the visual thing that Sphinx generates is this. And in particular, if you go to the reference section, I mean, I wrote motivating examples and all of the things you have to do in order to convince someone to use your product. Not all of them, but some of them. And there's this module geometry, and here are the classes that are in the module of geometry. And here's our old friend snapshot, and it's got, among other things, init. And this is the thing that I quoted. You notice it's incomplete because Sphinx has a bug in it. And never mind that. And I'm not Sphinx. SWIG has a bug in it that it garbles these. So it's supposed to have, that is supposed to look like this. This is the correct way that's supposed to look like. And I have complained about that bug, and it's not fixed yet. But at least the SWIG people, maintainers, know about it. Okay. There's still a lot more writing to be done, and there are links in my code that I made work at one point to the existing original handwritten HTML documentation for SST, and there were links from each of the reference documents in Sphinx to my old HTML, and those no longer work, and I don't know why. So it's a work in progress. Packaging, this is something I haven't done yet, but it's at the think and learn about it stage. Anyone who wants to volunteer information about this, I think I know how to do it. I just haven't gotten to it yet. As it'll be packaged as a wheel, which is a sort of the standard way of doing a package like this that's based on compiled code. And distributed via Conda. Because Conda rather than PyPI, because Conda has stuff other than Python in it. And PyPI is just for Python primarily. And that's where this project is. So if anyone has questions or comments, I got through this in less than an hour. So I'd be happy to address any questions that anybody has. I can't see hands raised or anything, so let me know, please, somebody.
I'd say, folks, there's just a few of us, just, open your mic and call out.
Well, okay. I was hoping for some feedback, but maybe I'll get some from what's posted online.
Yeah, we'll pop the video up. Send the slides to me too, Bob.
Yes, I will. The links to the other documentation won't work from the slides because those are directly to files on my disk, but that would be walking a thin line at the edge of what I'm allowed to do anyway. So it's just as well they won't work. If I gave you links to the full documentation.
Yeah.
That's it.
Okay.
Fantastic.
Yeah, thanks, Bob. Good presentation. Well, do we have any questions? Okay, I guess with that, let's go ahead and end the recording.
Here it is.
Okay, I'll end the recording.